Given, two distinct nodes P and Q in a binary tree, where every node stores a pointer to its parent and the root's parent is null. Return, their lowest common ancestor, the deepest node that has both P and Q as descendants, where a node counts as a descendant of itself. Constraints, between 2 and 10 to the 5th nodes, all values are unique, and P is not equal to Q. In this example, P is the node with value 5 and Q is the node with value 1. Walking upward from P you hit 5 then 3, from Q you hit 1 then 3. The first node seen on both upward paths is 3, the lowest common ancestor. Example 2, P is the node with value 5 and Q is the node with value 4. Ancestors of P include 5 and 3. Walking up from Q you visit 4, then 2, then 5. The first node that appears in both upward walks is 5, when one target is an ancestor of the other, that ancestor is the lowest common ancestor. Each node remembers its parent, so there is no need to scan children for this problem. Imagine standing on P and on Q, each of you sits on a single staircase of parent edges that leads to the root. Everything off those two staircases can be ignored. If both runners climb one parent edge at the same speed, a shorter chain hits the root first. They are not guaranteed to occupy the same node on the same beat, so a naive lockstep climb does not directly reveal the meeting point. You first need to cancel that length gap. The usual fix is a path swap. When your climb would leave the root, teleport to the other starting node instead, and keep climbing. Each marker still moves one parent per step, but the detour makes the combined route length the same on both sides. The very first node where the two markers meet is the lowest common ancestor. Picture two vertical routes to the root. From P the chain has 5 nodes, from Q only 3. Advance both pointers one parent at a time. Because Q sits higher in the tree, pointer B reaches the root while A is still 2 steps below it. Same speed climbing alone does not guarantee a meeting, the depth gap has to disappear. The constant space trick, when a pointer has no parent, send it to the opposite starting node. Pointer B has just reached the root, so on the next step it reappears at P while pointer A steps from its current node toward the root. Later, when pointer A reaches the root, it will jump to Q the same way. Each pointer still does one step per tick, but each full tour is path from P to the root followed by path from Q to the root, and vice versa, so the combined walk length matches on both sides. From here the two markers stay in lockstep. They have both paid off the length difference by wrapping through the other starting node, so the next time they occupy the same node it will be on the same beat. That shared node is exactly where the upward paths first meet, the lowest common ancestor. The loop exits when the two references are equal, that node is the lowest common ancestor. Only 2 pointers were stored, so extra space stays constant, and we never computed depths or tree height explicitly. Let n be the number of nodes in the tree. Time is linear in n in the worst case, each step follows one parent edge, and each pointer covers at most the 2 root ward chains before they align. Extra space stays constant, we only keep 2 references into the tree plus fixed local variables. Pseudocode for lowest common ancestor with parent pointers. The function takes nodes P and Q. Pointer A starts at P. Pointer B starts at Q. Repeat while the 2 references differ. If A still has a parent, move A upward. Set A to that parent. Otherwise A is at the root, so jump A to Q. That is the swap, continue the walk from the other starting node. If B still has a parent, move B upward. Set B to that parent. Otherwise jump B to P. After both branches, loop again until A and B name the same node. That node is the lowest common ancestor, return it.